Hi everyone, my name is Connor and you're very welcome to this Saturday session for Junior Cycle Science, and the topic for today is going to be electricity. So as we start to move through the content for electricity, we're going to have a look at some theory behind it, and we're also going to apply our knowledge and have a look at some exam questions as we move throughout it. And right at the very end, I'm just going to show you the ExamRevision website where you can access all of the resources from today and more. Now, when we talk about electricity, we need electricity for a variety of different reasons. Some of these being lighting up our homes, heat, having showers, and much more. Now, there are two types of electricity. We have static electricity and we have current electricity, and you will look at both, or will already have looked at both, as part of your Junior Cycle Science course. So as you were growing up, you were probably working with static electricity, you just didn't know it. So static electricity is a buildup of charge in one place. So if you can remember, if you ever got a balloon and rubbed it against your hair and then held it up against your hair would stand on your head. Similar, if you rubbed a balloon on your jumper, put the tap on and then held the balloon towards the water would look like it was moving out away from the balloon and not flowing in a continuous line. They are all examples of static electricity. So when the buildup occurs, the charges will push away from each other as they want to get away from each other. So we can see that over here, the like charges are repelling. So when you rub a balloon against your hair, the negative charges that were on the balloon will be attracted or passed to the positive charges that are in your hair, and this is going to cause your hair to rise. So that's static electricity, a buildup of charge in one place. Current electricity then, on the other hand, is a flow of charge from one place to another. So it's not a build-up in one place, we have the flow of charge going from one place to another place. Current electricity needs to be powered by a power supply, and one which you would have come across is just a battery or a battery pack, which we can see over here on the right hand side, so a simple form of a power supply. And it also needs to have a full complete loop, which has a starting point and an end point. So at any point, if there was a break along the circuit, the flow of charge is going to stop. So it has to be a continuous loop. Now, just on that, we're just going to talk about two different types of current when we mentioned current electricity. We will come back to this towards the end of the presentation as well. It's just to mention it now. So current electricity can flow in two different ways. They can be referred to as alternating current. So this is where current flows in one direction for a while and then can go the opposite direction. So that's what the diagram down here represents. Can go in one direction for a while, but then can go in the other direction. Or we have direct current, and this is current that flows in one direction only. And sometimes they're referred to as AC and DC. So AC standing for alternating current and DC standing for direct current. Now we're going to move our discussion to the idea of a circuit. And an electrical circuit is a path in which electrons from a voltage or current source will flow. Now, if you haven't already built circuits as part of your Junior Cycle Science course, you will before you get to the end of third year, and a circuit might have looked exactly like this. And we would have drawn diagrams of those as well, and we'll see how to in a couple of minutes. Now, for this circuit to work, it has to be the full continuous loop, as we've mentioned before, and it also needs to have its source of electricity, such as a battery. Now, when we're drawing circuits, we don't draw a sketch like we would a 3D sketch maybe in art. We draw simple line diagrams to keep things as easy as possible for ourselves. And each bit of equipment which you might use is going to have a certain symbol which we can use. Now, we're only going to look at a couple of them here, but all of the ones which you will come across as part of Junior Cycle Science are here. So if we see this one here, imagine you were looking down on top of a bulb. It's going to be a circular shape, and we just put two lines through it as well, an X shape. That's our lamp. A buzzer, this is it here. Okay, so if we were looking down on top of the buzzer, it kind of looks like a bell that we're going to press down on. That's the buzzer. If we draw a line, that's going to denote or depict a wire. Our switch, so the switch is up there, we push that down, that's our switch. And then this is our battery. There is a 2-cell battery, but we can just worry about the 1-cell battery for now. So we have one bigger line and one smaller line. That's our battery. And then we have a couple more bits of equipment over here. So the V is a voltmeter, A is ammeter, and if you see this rectangular shape here, that's the resistor, because it kind of resembles what the resistor looks like over here, which you might have used. So the big ones we're going to look at here were the bulb, the buzzer, the wire, the switch, the battery, and the voltmeter, ammeter, and resistor. And we will go to all of those now individually to see what they do. So when you're building your circuit, we're just going to have a quick glance down here at the circuit. We're not going to worry about the difference between series and parallel yet, but we can see here straight away, that's my battery over here, the same symbol. This line here the whole way around, that's my wire, exact same thing over here. So we're just getting used to what the equipment looks like. And this here is my 2 bulbs, and over here I have my 2 bulbs as well. That's all we have in these particular circuits. We could add in more equipment if we wanted to. Now, the series and parallel circuit. A series circuit is going to have one path for current to travel. So we can see if we were to move around here along our circuit, there's only one way for the current to flow. Okay, so we'll go through lamp 1, lamp 2, and that's it. Now over here, a series and parallel, that's going to have 2 or more paths for the current to travel. So we can imagine here, once we get to the junction, the option is to go through lamp 1, or we'll continue down and we can go through lamp 2. And then go right back up to the start. But the difference here, the series circuit, there's only one way in which the current can travel. In the parallel circuit, there's 2 or more paths for the current to travel. Now, if we have a look at the series circuit in more detail, you probably would have seen an example of series circuit around Christmas time. And this is because the series circuits can actually be problematic around here, because if the first bulb was to stop working, the current would not be able to go to the next one because the circuit is broken. And we can see that down in the diagram down here. So if lamp 1 wasn't working, the circuit is going to be broken, the current can't pass on to lamp 2. So any lamp that was after that first one is not going to light up. So older Christmas lights in particular used to use series circuits, which was very time consuming, because then if there was a broken one, you had to go and check all of them individually to see which one needed to be replaced for the lights to be working again. That's why Christmas lights nowadays would look more like this. You can see all the multiple wires going into it, and that's because they have parallel circuits. And parallel circuits are more beneficial because even if one bulb was to break, it still means that the current can flow. There's more pathways available to it, and all of the rest of the lights are going to work. So there's just a difference between series and parallel circuits in real life. Now we're going to talk about electrical conduction. So substances that allow electrical particles to pass freely through them are called conductors, and metal is a good example of a good conductor. Substances that don't allow electrical particles to pass freely through them, however, are called insulators, and plastic is a really good example of an insulator. So we're going to see a quick exam question here, just summarising everything that we've looked at so far. This came up on a junior cert exam a couple of years ago, and we'll talk through it. We'll see the marks that are available for each different question. So a battery, such as the one in a mobile phone, uses chemical reactions to make electricity and is a source of direct current. What is direct current? So we know that's current that flows in one direction only. If it could go in both directions, that would be alternating current. So that would have been 3 marks right there. The other type of electric current is supplied to our homes by electricity suppliers. Name this type of electric current. Well, we've actually just mentioned that there. That's alternating current. And again, that would be 3 marks there. What is the main energy conversion that is happening when a mobile phone is being charged? So we could have a look and say electrical energy to chemical energy. Because our batteries are full of chemical energy. So that was 3 marks there again. And now we're going to go down to the part C of the question. So the symbol shown on the right is that of a bulb. So it looks slightly different from the one we've seen earlier. You might have seen one that looked like that before, but exact same thing. In each of the spaces provided, draw 2 bulbs so that they are arranged in series and in parallel. So the one in series that we've seen before, we're going to have our battery, we have our wire, and our series circuit is going to look something like this. So there's my 2 bulbs, and my parallel one is going to look something like that. Okay, so the one in series over here, we've 1 bulb after another, and the one in parallel, we have 2 possible routes for the current to flow in. Now, we're going to get into a discussion now of voltage, current and resistance and look at the calculations associated with those. It's a very common exam question to come up, and so too is being able to analyse data and draw graphs based on it. So voltage is also called potential difference. So if you ever see the words potential difference, it just means voltage. So they're interchangeable with each other. Important to know that they're the same thing. Now it's easy to remember what's used to measure voltage because the first part of voltage is volts and it's measured by a voltmeter. And we can see that this diagram over here is a voltmeter because it has the letter V in it. And that's important to know because there is other pieces of equipment that look very similar to it. So we look at the letter that's on the front. So a voltmeter is used to measure voltage. And again, quite easy. What's the unit of voltage? It's just the volts. So current is a measure of how much charge is flowing at any point in a particular circuit, and it's measured using an ammeter. So this piece of equipment over here looks very like the voltmeter, but we know it's an ammeter because it has the letter A in here in the center. And the ammeter is used to measure current, and the unit of current is the amperes. And we can abbreviate that down to amps. More than often we just use amps rather than amperes. And resistance finally, so the electrical resistance of an object is a measure of its opposition to the flow of electric current, so trying to slow it down. So resistance is measured using an ohm meter, and resistance is measured in ohms. And ohms also has the symbol omega, which is the symbol down here. So omega and ohms. And over here is an example of an ohm meter. You can also use a multimeter. So a multimeter would look very like the ohm meter here. A multimeter measures multiple things, so you can use it to measure voltage, current, and resistance. But this one over here is just an ohm meter and it's used only to measure resistance. Now, voltage, current, and resistance have a very specific relationship with each other. And that all comes back to Ohm's law. So Ohm's law states that voltage is directly proportional to current. And the calculation that's most commonly used for that is that V equals IR. We'll come to each one of those in a couple of seconds. Now, we're going to use this triangle over here to remember all of the different calculations for voltage, current, and resistance. If you're trying to remember the specific order of the triangle, it looks very similar to one you might have used for distance, speed, and time before in Dad's silly triangle. We're just going to remember that Ohm's law is a very important relationship. So very important relationship. So V stands for voltage, I is current, and R is resistance. So within the triangle, we have our very important relationship, voltage, current, and resistance. Now this line under here just means divided by, and we have multiplication symbol there between current and resistance. So we're going to see how we can use that triangle now to actually calculate the voltage, the current, and resistance. So if you want to calculate voltage, we cover up the letter for voltage. So we're going to cover up the V. And what are we left with? We're left with current multiplied by resistance. And that's exactly what we have over here. Voltage equals current multiplied by the resistance. So I'll rub that back out. We're now going to try and calculate the current. So we're going to cover up the current. What are we left with? If we're calculating current, it's the voltage divided by the resistance, which is exactly what we have here. Current is the voltage divided by resistance. And finally, if we're trying to calculate the resistance, cover up the resistance. What are we left with? Well, it's just the voltage divided by the current. And that's what we have here. Resistance, voltage divided by current. So they're the three most important things we get from that triangle. That's how we calculate voltage, current, and resistance. And really handy just if you learn off that triangle, because it will be really useful in an exam situation just to jot it down at the side of the page and help you remember our very important relationship. Now we're going to have a look at a couple of examples of calculating voltage, current, and resistance. So we know over here, how do we calculate the voltage? Well, let's cover up voltage. What are we left with? It's the current times the resistance. So let's have a look. What voltage is required to create a 3 amp current in a circuit with a resistance of 3 ohms? So 3 amps, that's the current, 3 ohms, that's the resistance. So we'll write down our formula. We know that the voltage is equal to the current times the resistance. So the voltage is equal to 3 because the current was 3 up here. The resistance was also 3. So 3 by 3 is 9. And don't forget the unit for voltage is the volts. So 9 volts. Exact same thing here. We're going to try and measure the voltage. So what's our formula for voltage? Well, the voltage is equal to Let's cover up voltage over here now. It's the current times the resistance. You can use the symbols for current and resistance if you want. So if you wanted to simplify that for yourself, you could just write down I by or straight away. Completely up to you. So what is the current? Well, the current is 4. The resistance is 5. So it's 4 by 5, which is 20. And don't forget the unit for volts is, or unit for voltage is the volts. So 20 volts is the voltage required there. And final one here on voltage, again we're calculating the voltage, so let's cover that up in our very important relationship. So I'm going to do the shorter version this time. So the voltage is equal to the current times the resistance. Our current is 2 from up here. Our resistance is 5. So this time we're going to need 10 volts. And that's all you need to know on calculating voltage. Current is slightly different. So if we want to calculate the current, we're going to cover current in our very important relationship. And we can see that we're left with the voltage divided by the resistance. So voltage divided by resistance, we're given all the information in the question. We know that the voltage is 9. We know that the resistance is 360 ohms. So we do 9 divided by 360, which is 0.025A. You could also write the word amps there if you wanted to. So 0.025 amps. So it is quite a small current, but that's absolutely fine. You can get a number that's that small. So we'll try this one. Looks a little bit different because all of the information that we need is actually in diagram form rather than words this time. But we're going to follow the exact same steps. So how do we calculate the current? Well, we're going to cover current up over here. And we know that current is found by dividing the voltage by the resistance. So what is the voltage? Well, the voltage is 12. That's in the diagram. So 12 volts divided by 6 ohms because the resistance was 6. And 12 divided by 6 is 2, and we know that the units is amps. So capital A there for amps. And the final one here on current. So again, we're going to cover current up in our diagram. How do we calculate the current? Well, the current is equal to the voltage divided by the resistance. Voltage this time is 18 volts. Resistance is 3 ohms, and 18 divided by 3 in our calculators will give us 6. And don't forget that the units for the current is amps, so we put in a capital A there as well. So the final one we have to look at now is resistance. And if we want to calculate resistance in our very important relationship, we're going to cover resistance up in the diagram, and we can see that we're left with voltage divided by current, which is exactly what we have here. So what resistance causes a 0.4 amp current to flow when a 1.5 volt battery is connected to a circuit? So the first thing we're going to do is, how do we calculate the resistance? The resistance is the voltage divided by the current. Now, what is the voltage? Voltage is 1.5, which we have from up here. Current is 0.4, which we also have from up here. Use your calculator to calculate that, and we get 3.75 ohms. This one we haven't seen before. We actually have all the information we need in table form this time, but we're going to follow the exact same steps. How do we calculate our resistance? Let's cover resistance in our diagram, and we know that resistance is equal to the voltage divided by the current. Now, we're going to look at the table up here, and we can see we have 5 different values for the voltage and 5 different values for the current. It doesn't matter which one of those you pick, okay? Just make sure they're paired off with each other. I'm going to do 2 of them just to show that you actually get the exact same answer. So I'm going to pick the first one, and we'll also do the last one over here as well. So in the first one, what's the voltage? Well, it's 2. What's the current? It's 3.6. And when we work that out, we will get that that's equal to 0.56 ohms. Exact same way over here. What was the voltage? We had 8. The current that was linked to that was 14.4. And if you work that one out in your calculator, you will also get 0.56 ohms when we round up. So it doesn't matter which set you pick once they're linked to each other. You can't randomly pick a voltage of 2 and pair that with a current of 10.8. They have to be linked to each other, but it doesn't matter which ones. Exact same idea here. We have a table. I'm just going to do the 1 this time because we will get the same answer no matter which one we pick. I'm just going to pick the second one here. So how are we calculating our resistance? Let's cover up resistance in our very important relationship. And the resistance is equal to the voltage divided by the current. Now the voltage in this case was 1. the current was 0.05, and when we work that out, we will get that the resistance is 20 ohms. Okay, so quite a big resistance in this case. We have a resistance of 20. Now, we've already mentioned this already, but just to recap, current electricity can flow in two different ways, and they're termed as alternating current, also known as AC, which means that the current can flow in one direction for a while and then can go back the other direction, and that's this diagram down here. Whereas direct current, also known as DC, can flow in one direction only. So we're going to have a look at a couple of exam questions here based off of that, and we can see that this kind of incorporates everything that we've looked at so far. So the circuit diagram below shows the equipment used to measure the current through and the potential difference across the resistor or. So we're told already that this here was the resistor. Name the piece of equipment labelled A that is used to measure current. So if it's measuring current, the letter A is giving us a bit of a hint there as well. That's an ammeter. And we will get 3 marks for that. The second question there, name the piece of equipment labelled V that is used to measure voltage. So again, the V is giving us a hint. That's the voltmeter. We can see that up here. And again, that would be worth 3 marks for us. And now we have a calculation. So the current is 2 amps and the voltage is 6 volts. In the table, write the letter X beside the value of the resistance of the resistor. Now, before I answer this question, I'm just going to recap my memory. How do I calculate that? I can't fully remember, but I do know that I have a very important relationship. So what are we trying to calculate again here? We're trying to calculate the resistance. So let's cover up the resistance. So that means the resistance is equal to the voltage divided by the current. And now that's really going to help me. Because look, I have my 6 volts, I have my 2 amps for my current, so it's going to be 6 divided by 2, which is 3 amps. Let's have a look at my table. Is one of those answers applicable? And I can see, yep, it absolutely is. That's the same answer as I had got over here. Now be very careful, it's not a tick. We have to put the letter X inside the box. So I go back over and put an X in there, and that will get me my 3 marks. Now, part 4, in the table, write the letter U beside the unit of measurement for resistance. And we know that that's ohms. So it's not kilowatt hour, that's more to do with power. So we're going to put the letter U in here beside the ohms. Now, a couple more pieces of equipment that we're going to have a look at, and then we'll have a look at another exam question to do with electricity. So these are our diodes. So a diode is an electronic component that conducts current primarily in one direction. And that's what the arrow down here signifies. So it's flowing in one direction only and goes in the direction that the arrow is pointing. So that's what it says here. The arrowhead points in the direction of the current flow. Now, you might have heard a diode in terms of light emitting diodes, or LEDs. They're a form of light. And an LED is a light emitting diode. An LED will only allow current to flow in one specific direction through it. And when current passes through it, light is going to be emitted. So we can see the symbol for an LED, or a light emitting diode, is very, very similar to the diode. It has our arrow, but to signify a light emitting diode, we just have arrows pointing out of it just to show that there is light coming out of it. So that's our LED. Now, where are LEDs, or light emitting diodes, actually used? They have a variety of different uses. So they're used in traffic lights, so your red, orange and your green lights. They're also used within TV and laptop displays, and also sometimes used within bicycle lights. A light-dependent resistor then, on the other hand, or an LDR, that's a resistor that changes its resistance depending on how much light is falling on it. And if we compare that to the symbol that we had for a resistor, we can see we still have the rectangle that the resistor had, but it needs light shining on it. It's light dependent, and that's what the 2 arrows pointing in towards it mean. So it needs light. The arrows are not pointing out of it like the LED, they're pointing into it because the LDR needs light. Now, one of the main uses of LDRs is in streetlights. So we know that as it starts to get dark in the evening time or night time, the streetlights automatically turn on. There is nobody required to actually physically turn them on. And that's where the LDRs come in use. So when it's dark, there is high resistance present in the streetlights. So for Ohm's law still to hold true, for that still to work, as the resistance gets higher, the current has to get lower. So because the current is getting lower, that's automatically going to switch on a transistor, and that will amplify the current, and that's when the light will be emitted. So it all comes back to Ohm's law. Because of Ohm's law, as the resistance gets higher at nighttime, the current has to come back down, directly proportional relationship. This is going to switch on a transistor, which will amplify the current back up, and then the light will start to be emitted because of that transistor coming on. So here's another exam question which has come up before. It was quite a long one and involved a graph, which we're going to have a look at now. And it says here, a student used the circuit shown to investigate the relationship between potential difference across a resistor and the current flowing through it. So the results are given in the table below. So we have our values for our voltage and we have the values for our current. So draw a graph of voltage against current for these results. So I'm going to draw this, showing you how to plot it. Don't have a ruler that I can use right now, but you will use a ruler to join all your points together because it has to be a straight line. But our voltage is 2 and our current is 3.6. So we're going to go to voltage of 2 and go across 3.6, which is going to give me a point roughly there. Voltage of 4, current of 7.2 will be roughly there. 6 and 10.8 will be there. 8 and 14.4 will be there. And finally 10 and 18 will be exactly there. Now with a ruler, I'm going to join those together. Hopefully we get a perfect straight line. And there we go. And when we're drawing a graph of this, we should always end up with a perfect straight line. And that's actually going to answer our next question there as well. What is the relationship between voltage and current shown by your graph? And it's directly proportional. So the increase at the same rate. As current increases, so too does voltage. And it's at a constant rate. It's directly proportional. So we should always end up with a perfect straight line. So calculate the resistance of the resistor. So again, we're going to do our very important relationship over here just so we can remember how to calculate the resistance. We're going to cover up resistance. So the resistance is equal to the voltage divided by the current. And just like the examples we've seen earlier on, you can use any examples in the table or any data values once they're linked together. So if I'm picking the 4 for the voltage, I have to pick the 7.2 as well. And that's the one I'm going to pick. So I'll circle them up here just so I know which ones I'm using. My resistance is equal to my voltage, which is 4, divided by my current, which is 7.2. And when we pop that in our calculator, exact same as the one we did earlier on, 0.56 ohms. Now that is a very common question that does come up on electricity, where you have to graph the voltage and the current, state that the relationship is directly proportional, and perform calculations based on the data that you have. Now before we finish up, I'm going to show you around the ExamRevision website where you can access video tutorials, quizzes, presentations, and anything else you might need to help you with your study of junior cycle science and other subjects at junior cycle as well. So when you log into the ExamRevision website and make an account, if we click into video tutorials, you will see that it's broken down into the 4 different units which we have. So we have our biological world, earth and space, physical worlds, and chemical worlds there as well. So we're going to click into physical worlds because that's what we're looking at today. So it's broken down into all of the different units that we have. So physical world 1 to 8. And if we want to have a look at the electricity and circuits, which we were looking at, we'll click into physical world 5. So we have a video there on electricity and circuits, voltage, current and resistance and their calculations, electrical power, and also LEDs, LDRs and energy efficiency. We do have quizzes linked to each topic as well. So if we click into that, we'll see that we have a multiple choice quiz, which you can use to test your knowledge based on electricity. And that's the same for all of our topics. So if we click into another random one, we maybe go into biological world this time. If you wanted to study human health, we click into BW6. We see there we food and nutrition, bacteria, viruses and fungi, and genetic disorders. And again, we can click into the quiz and there's a quiz for you there to test your knowledge on. There's also PowerPoint presentations on each of the topics, so you can click into whichever one you want. It'll automatically redirect you to a PowerPoint and you can flick through it to find out all of the information which you might need on particular topics. And we also have our exam builder as well. So if you press build your exam in any of the topics, because we're in biological world 6, it will show us all of the questions to do with biological world 6, which was human health. You can add them to your exam as you scroll down by pressing on the plus button. So we'll add 2 questions just to start off with. We'll give it a title. And you can now download your questions and also your answers there as well, which is the marking schemes that would have been used. So if you want to find out more information about exam revision, just go to examrevision.ie. You can make an account, and if you scroll down to the bottom, you'll see there's information there about plans and pricing. It used to be a once-off fee, but now you can sign up with a monthly subscription as well. And the more subjects you choose, the bigger of a discount you will get. And if we just have a quick look here, we can see that there's lots of subjects for you to choose from. We've junior cycle business, we've geography, we've home ec, we've maths, and we also have science as well. So keep an eye on our YouTube channel. We're going to be running these Saturday sessions every Saturday throughout the year for all of those junior cycle subjects. So make sure and set a reminder for yourself. Every Saturday, 11 o'clock, you'll be able to find us here. I hope you've enjoyed it, and I'll see you all again soon.